The first topic we're going to talk about in statics is going to be force vectors. But before we can start to talk about what force vectors are and analyze these systems, we need to determine what vectors are, how vectors are different than scalars, and what are some mathematical operations we can perform with vectors. So we have to start to build up the tools in our toolbox. Now, let's start by defining what a scalar is. A scalar is going to be any quantity that can be expressed by a magnitude. For example, the temperature outside. The temperature outside is 75 degrees Fahrenheit. That 75 is my magnitude. It tells me how much of my temperature I have. So if I say 75 degrees Fahrenheit, I don't need to explain anything else. You know exactly what I mean. If I say the mass of a rock is 50 kilograms, you know that 50 is how much mass it has. Now, vectors are a little bit different. Vectors, while you need the magnitude, you need to know how much of the vector we have. The vector also needs a direction. So a vector is any quantity that can be expressed by a magnitude and a direction. Now, we are going to express vectors, and we're going to draw vectors by using an arrow. And what this arrow is, it needs to be able to figure out what the magnitude is. It needs to be able to express the magnitude and express the direction. So the magnitude is easy. The magnitude is just going to be how long this vector is. The direction, we need to figure out two things. We need to figure out which way is this arrow pointing. So to do that, we figure out the head of the vector. The head of the vector is going to be the arrowhead. The other side down here is going to be the tail. And we need to figure out which direction this arrow, what angle this vector makes with a reference point. Normally, it's going to be the positive x, positive y axis, but it can be any axis that we want, and we want to figure out what this angle is. If we had extended a line through this arrow, through this vector, and we extended this line infinitely, this line would be called the line of action. And so what it really is that the angle that this line of action makes with what we're trying to measure this vector with respect to. So here, with this angle in the direction that the head's pointing, the orientation that the head is pointing, we can figure out the direction. So now we have expressed the magnitude and the direction. Okay, so now that we can graphically express these vectors, let's look at what we need to do any type of mathematical operations with them. Let's start with scalar multiplication and division. So with scalar multiplication and division, what we have, let's say we have an arrow, a vector, and we have a vector of a length of 1, and let's call this vector A. If we multiply this by 2, what's going to happen? It's going to scale our vector, so the new vector is twice the length of our old vector. So this is A, this is 2A. We can do the same thing. We can multiply it by 3, and it's going to scale our vector, so it's 3 times the length of our original vector. But notice it's not changing the orientation of the vector. The vector is still pointing in the same direction. If we wanted to make it smaller, we're going to have to multiply by a number less than 1. And that's how we do division. So if we had done my vector A, and we had divided my vector A by 2, then this is really like multiplying it by 0.5. So division is just a special form of scalar multiplication. So we're going to do 0.5 times A, and what we're going to get is a vector that's half the length of the original vector A. And notice, again, the direction of that vector has not changed. Now we can switch the direction of the vector if we multiply by a negative sign. So let's say we multiply -1 times a. You're not going to really see it like this. You're going to see it a lot more, just times a negative a. But what that's doing is that's saying that we're going to turn our vector around. So the head is going to be in a 180 degree. It's going to be rotated 180 degrees, but the length is not going to change because we're multiplying it by a 1. If we had multiplied it by a -2, the head would still switch 180 degrees, and then it would scale so it would be 2 times as large as our original vector. So the negative sign is going to switch our vector 180 degrees. So that's scalar multiplication and scalar division. What about if we wanted to add 2 of these vectors together? So let's talk about vector addition. So for this, let's say I'm going to have some vector A. I'm going to make it a little bigger. So I'm going to have some vector A, and I'm going to have some vector B. So what if I want to add these 2 together? So how do I do this? Well, first, let's do A plus B. I'm going to take my vector A. I'm going to go from the tail to the head, and then I'm going to place vector B, tail to head. So vector B, tail to head, is like this. And I'm going to connect a line, another vector, from where I started to where I ended. And this vector right here is going to be my resultant vector. And what I can do, so if this is A, and this is B, I can prove that if this is going to be equal to B plus A, and that they're both going to be equal to my resultant. How do I do this? Well, instead of going A plus B, let's start with what B is. So we're going to do B. I'm going to then add in A. And I'm going to get to the same point. So what I did was, with vector addition, it doesn't matter if I do A plus B or B plus A. I'm going to get the same result, and that's going to be my resultant. Now, if you look closely, this right here is going to be a parallelogram. And when we start to analyze these systems, we're going to use properties of parallelograms in order to be able to figure out what angles are, side lengths are, all types of good stuff. And if you look really closely, you'll see 2 triangles. So this top triangle right here, and a bottom triangle right here. So using parallelograms and triangles, with triangles, we'll use law of sines, law of cosines. We'll be able to figure out a lot of these force systems. Now, in addition to vector addition, we can look at vector subtraction. When we look at vector subtraction, let's use these same 2 vectors. And let's do A minus B. So what is this? Well, this is really an A plus a -1 times B. And we know how to handle this case, right? We looked at it right up here. We know that that negative sign is going to switch it 180 degrees. So A is going to stay the same, but B is going to switch 180 degrees and point in the other direction. So then when we do A plus a minus b. It's really this plus this opposite b. And our resultant will be the yellow line, this line right here. And this is A, and this is B. Now you can see if I did B minus A, I would not get the same answer. So B would bring me this way, and then a minus A would bring me back over here. So subtraction is not commutative. Now finally, the last thing I want to go over is vector resolution, resolving a vector. Let's say I have a resultant. I have this R term right here. And I want to figure out what components are along two different axes. So these can be any axes that I want. Let's say that I want to figure out what it is along this, and we'll call this y prime, and along this, and we'll call this x. So I want to figure out the components of R along the x and y prime axes. How do I do this? I start at the head of the vector, and let's make a parallel line with x until we cross the y prime axis. So that becomes one of my vectors. Let's do the same thing. Start at the head right here. Do a parallel line with y, and that becomes another one of my vectors. So if this was just say D, and this yellow line was C, we can see that C is the component along this x. So C is also over here. D is the component along the y prime. So D is also over here. And we see exactly what we saw up with this addition. If we do D plus C, we're going to get to R. Or if we do C plus D, we're going to get the same resultant. So this is if we break this resolving vectors are if and when we break up our vectors into components along different axes.